Good afternoon, ma'am. Myself, Meghana. I am from CSE B section. My roll number is 234G180593. And today my topic is synchronous down counter 2-bit and 3-bit. Before going into the topic, we know what is counters. Counters are sequential circuits that store and count digital places in a specific manner. Counters can be categorized based on how they operate and the way they handle clock signals. Below are the primary types of counters. There are two types of counters: asynchronous counter and synchronous counter. Synchronous counter. Before going to the topic, we know what is synchronous counter. A synchronous counter is a type of digital counter in which all the flip-flops means memory elements are clocked simultaneously. This means that each flip-flop in the counter receives the same clock signal and their state changes at the same time in synchronization with the clock pulse. These contract is asynchronous counters where flip-flops are triggered one after another in a chain-like fashion. Asynchronous down counter counts down in the binary form of a specified maximum. Below is a detailed explanation of both 2-bit and 3-bit synchronous down counter, states diagrams, like execution tables, logic circuits, and timing diagrams. In synchronous counter, there are two types: synchronous up counter and synchronous down counter. And our topic is synchronous down counter. Synchronous down counter is a digital counter that counts downward with each clock pulse. In a synchronous counter, all the flip-flops are triggered simultaneously by the same clock signal, and the count decreases on each clock pulse. The main difference between a synchronous up counter and down counter is the sequence in which the output changes. In the case of down counter, the binary numbers are counted in decreasing order. For example, 3, 2, 1, 0. For 2-bit down counter means the order is increased from up to down. In 2-bit down counter. 2-bit synchronous down counter. To design a 2-bit synchronous down counter, we need to select appropriate flip-flops and establish a truth table. The design will also require logic gates to implement the necessary combinational logic for state transitions. The 2-bit synchronous down counter consists of two flip-flops. It counts from 3, 11 in binary, down to 0, 0, 0 in binary. The design utilizes combinational logic for state transitions, ensuring that the output reflects the current count accurately and synchronously with the clock signal. Here the diagram of 2-bit down counter. We consist of 2 bits, two flip-flops with Q0 and Q1. And the flip-flop we use it is JK and the clock pulse. On the downside, we know about what is that diagram. The diagram, the states transition as follows: 1 1 1 0 0 1 0 0 1 1. Circuit design. How the circuit is designed: by using the above components, the needed 2T flip-flops, FF1 for Q0, FF0 for Q0. Combinational logic determine the T inputs based on the current states. Connections. Connect Q0 to T input of FF1. Connect a contact logic high 1 to the T input of 2 clock signal. Connect a common clock signal to both flip-flops. We can see the truth table for the 2-bit synchronous down counter. 2-bit synchronous down counter truth table. We noted that clock pulse outputs means Q1 and Q0 and the decimal equivalent. The give clock pulse 0 and the output will be produced 1 1. And the decimal equivalent value is 3. And similarly 1 2 3 we given means the output will be produced 1 0 0 1 0 0. And here we can observe that the output will be decreased from high to low, means 3 2 1 0. Flip-flop selection. We can use T flip-flops or JK flip-flops for the design. Here is a basic implementation of T flip-flops. Logic equation. To create the logic for the flip-flops, T flip-flop input equations: T1 for Q1, T1 equals to Q0, T0 for Q0, T0 is equals to 1, means T0 is always taken. Next state logic. When Q0 is equals to 0, Q1 stays the same, T1 is equals to 0. When Q0 is equals to 1, Q1 toggles T1 equals to 1. Timing diagram. A clock cycle 0, initial state is 1 1. At clock cycle 1, state changes to 1, 0. Um, at clock cycle 2, state changes to 0, 1. At clock cycle 3, state changes to 0, 0. At clock cycle 4, state wraps around back to 1, 1. Uh, we, then the next is 3-bit synchronous down counter overview. A 3-bit synchronous down counter expands the counting range from 7 to 0 with the 3 flip-flops. It can represent 8 states. This design is suitable for more complex applications requiring a larger counting range. And the diagram of 3-bit synchronous down counter is here we can observe that the 3 bits and we take JK flip-flops or any other flip-flops. Here we are observing that uh, these are connected by one. We know about the above diagram by downslide. Circuit diagram. Based on the derived inputs, the circuit can be built using 3 JK flip-flops for Q0, Q1, Q2, Q1, Q0. Logic gates for controlling the inputs. Input summary is J0 is equals to K1, K0 is equals to 1, J1 is equals to Q0, K1 is equals to Q0, J2 is equals to Q1, Q0, K2 is equals to Q1, Q0. On the operation is the counter will count down from 117.000 decimal and the wrap back to 11. Each state changes occurs on the falling edge of clock signal and all that simultaneously. And we also know the clock input is common for all flip-flops and the down counting will happen in synchronization with the clock pulses. Truth table. Truth table for 3-bit synchronous down counter is we can select the clock pulse 0, 1, 2, 3, 4, 5, 6, and so on. The output means in 3-bit synchronous down counter, we have 3 outputs, which is Q0, Q1, Q2. If we give 0 as input signal, we can produce that Q2 is 1, Q1 is 1, and Q0 is 1. And the decimal equivalent value of 111 is 7. If we give 1 as clock pulse signal, then the output will be produced Q2 as 1, Q1 as 1, Q0 as 0, and this binary number representation of this 3-bit down counter is 6. Similarly, 2, 3, 4, all we can produce the outputs like this, and the in synchronous down counter the increasing order we are observing the 7 6 decreasing order we are observing 7 6 5 4 3 2 1. Next, flip-flop inputs are the next state for each flip-flop Q2, Q1, Q0 determines the input J and K based on the execution table for JK flip-flops. The JK flip-flop execution table, when current state is equals to 0 and the next state is equals to 0, J is equals to 0, K is equals to X. When current state is equals to 0, next is 1 is J is equals to 1. When current state is 1 and the next state is 0, J is equals to X and K is equals to 1. When the current state is 1, all we can observe like this only. We will derive the inputs for each flip-flops Q2, Q1, Q0 based on the current and next states. Flip-flop Q0 least significant bit since Q0 toggles on every clock pulse alternate based 0 and 1 inputs. J0 is equals to 1 always toggles. K0 is equals to 1 always toggles. Flip-flop Q1 toggles when Q0 is 0. From the truth table, we observe that Q1 changes states on the falling edge of Q0. Therefore, J1 is equals to Q0. K1 is equals to Q0. Flip-flop 2 most significant bit. Q2 toggles when both Q1 and Q0 are 0. So the inputs from Q2 would be J2 is equals to Q1 Q0, K2 is equals to Q1 Q0, and the applications of These synchronous down counter is digital clocks. These are used in digital clocks, time or countdown applications. In digital clocks or watches, synchronous down counters can be used to count down seconds, minutes, or hours in rise time-based circuits. Frequency division. Frequency divisors means synchronous down counters can divide the frequency clock signal by specific factor. Um, this we can observe in event count in industrial control systems, event counters, digital signal processing means pulse width modulation. Synchronous down counters are used in generate price timing intervals for controlling the duty cycle in PWM signals. And the conclusion of the topic synchronous down counter is in synchronous down counter are essential components in digital electronics, offering precise and coordinate countdown capabilities in various applications. Their ability to simultaneously trigger state transitions with minimal propagation delay makes them ideal for real-time systems that require accuracy and efficiency. They are widely used in applications such as digital clocks, frequency division, event counting, memory addressing, and many other control systems. It is very useful for digital logics. And thank you, ma'am.